hit the top of the hour, so let's go ahead and get started. Again, we're going to be doing this in two parts. I'd assume at this point most people are connected. If you take a look at your GoToWebinar sidebar, you'll notice that there's an area where you can type in questions. As we go along, if you have questions, feel free to type them in there. We can see those questions and we'll try to answer them as we go or when we get to the Q&A portion. When we get to Q&A, if you have a microphone or you're using the telephone, you can raise your hand and we can call on you and we can have a discussion about anything that we've talked about. All right, so with that, let's go ahead and take a quick gander at the agenda for today. So we're really looking at today in four parts. The first, we'll review simulation analytics. Scott and I will walk you through some of the theoretical constructs for simulation analytics, what makes it different. We'll also talk about exploratory versus production CFD and how that fits into simulation analytics. And then we're going to do an end-to-end case study with Tecplot Chorus, and that's where we'll dive into detail as to how you can walk through using the application to address a couple of problem sets. Okay. Finally, we'll have plenty of time for Q&A, and we'll go ahead and make sure that we will unmute folks who want to ask questions. But if you have a couple of questions and you'd like to get some answers from us, please start typing those into the Q&A section. So with that, let's get started. So I think as we've talked about in the last two webinars, we talked about what makes simulation analytics different. And I think, Scott, we've talked about this a bit, but when we talk about simulation analytics, what really does make simulation analytics from typical post-processing approaches?
Well, I think the main difference is that you have these two levels of data with your metadata, which encompasses not only the inputs, the key inputs to your simulation code, but also you have the field data, the detailed flow data for CFD, for instance, can be quite large files that represent the details of the flow field. And in simulation analytics, you're actually analyzing those both simultaneously. Whereas, in traditional business analytics, you would be focusing only on the metadata.
And that's, I think a lot of people we've been talking to recently have access to some of both of these tools, but really nothing that's integrated together. That seems to be common.
That's correct, yeah.
So in that context, then, let's talk about perhaps what you really get out of that metadata and in the context of both surrogate modeling in general, but some of the things that people are looking at when in a production level environment, they're looking at these probabilistic methods.
Yeah, one of the main things, one of the main analytics features of Chorus is the surrogate model, and this is where you're actually generating a representation of your data between the points. It may be in the form of a response surface, which is a least square fit of a function, or it may be a kriging or other possibilities. And the three main things that this allows you to do, in addition to just plotting, which is one of the things we'll be showing you, is sensitivity analysis. So this allows you to quantify the leverage of your input variables on your output variables. Is this input does this output variable change a lot with a small change in the input variable, or vice versa? Analysis of variance would also fit in there. There's also probabilistic analyses that you would do. All your input variables in the real world would have some sort of randomness, and so an example of this might be the ensemble models that they use in weather forecasting, where they tweak the initial conditions and run the cases several times, and you actually analyze the ensemble of the results. And then these techniques can also be used to basically create a more robust and reliable design.
So that's certainly an area where we're seeing people apply some of these probabilistic methodologies. Although I think oftentimes we've talked about the use of Chorus and the need for this type of analytics for large sets of data, but we're also finding that people who are looking at one or two solutions, or well, maybe probably 3 or 4 solutions, benefit from the ability to do comparisons and to understand those sensitivities even on a small scale.
That's right. Now, the nature of statistics is you need a certain number to get statistical significance, but there's a lot of information you can gather from a small quantity. For instance, they do that in grid resolution studies to determine how much grid do I actually need. This would be before you start a large production CFD parametric study. There's somebody who's going to sit down and say, is 10 million grid points enough, or do I need 100 million grid points to actually get an accurate solution? And so, you only, in that case, will probably run 3 or 4 grid resolutions to make your decision.
Right. The ability to compare those can be very helpful.
Right.
So in this context, we're going to, today in our end-to-end walkthrough of a couple of case studies, we're going to start with the concept of how do you go from a series of solution files. In this case, they are CFD solutions, but they're not limited to that. If you can load the data into our core products, you'd be able to load that data in to Tecplot Chorus.
Absolutely. We have loaders for structural mechanics and, all sorts of groundwater. We have a lot of things that people use Tecplot 360 for. So, and if they can do that, they can load it into Chorus.
So in that context, we'll spend most of our time talking about how you analyze sets of information and do comparisons. And we'll also spend some time talking about how you can go from those metadata, or the integrated quantities, into something that you can make a decision on, in essence, those response surfaces or surrogate models.
Right.
So before we dive into the demo, I think it's probably worth spending just a minute on something that we're running into out in the industry. Is really the 2 basic types of CFD analysis we're running into, one being more exploratory versus production level. And Scott, we've talked about that. I think we've alluded to it, but maybe it's worth spending a moment on that. When you think of exploratory CFD, you talked about grid resolution. What other kinds of things might fit into this exploratory CFD?
Well, there's a lot of things involved. For instance, one of the goals is always to make sure, before you go start a large set of runs, is to make sure that you can get a stable solution. And it would be nice if CFD or other analysis codes were very robust. That isn't, in my experience, the case at this point. So you have to play with it a little bit on the particular geometries you're dealing with. And there's some things you might need to alter to get a robust solution. You might want to alter if you're running certainly an explicit scheme, but implicit schemes as well. You might want to alter your time steps. There may be a time step beyond which it's unstable. Boundary conditions are always an issue. If you have them, you need to get them set up correctly. If you don't have them set up correctly, you do not have a well-posed problem. So they're over-specified or under-specified, and you will not get a good solution. And then there's these knobs, if you will, in the codes, the smoothing parameters and upwinding techniques, limiters. All of these things are knobs that allow you to enhance stability, but they may also reduce accuracy. So you can't just crank them up. You need to be careful about that. On more the accuracy side, that you might need to try a few turbulence models. It may be that you normally run a Szilard-Almaris, but in this case, you need to run a two equation model because you're looking at plumes or something, or the plume is important. And then grid resolution studies, that's where you run at different grid densities, coarse, medium, fine, and then make a decision as to just how much grid you need. Is medium enough? Do you need to go fine in order to get the accuracy you need?
And that's certainly an area where I know that there's a lot of research being done, and ultimately you want to run the smallest mesh you can get away with just because it's faster.
Right. If you're going to run 1,000 cases or 10,000 cases, you don't want to be running billion cell mesh if you can get away with 10 million. On the production side, of course, that's where you're just trying to do a whole bunch of runs, and you'll start with some sort of design of experiments, maybe a full factorial design, or for a small number of parameters, or something a little more elaborate if you're doing like a Latin hypercube for. And the design really just tells you which cases to run, which set of input variables. And then, you use it for performance prediction or optimization, maybe. That's maybe not a design of experiments. That may be, one of the gradient methods, or and that's where you're trying to actually solve your problem in terms of getting a better design.
So in this context, let's then switch gears a little bit, and let's look at two models. The first model is kind of a hybrid. It's in many ways exploratory, although given the fact that it was looking at multiple results, you might say it kind of bridges that gap between going from exploratory to what we'll call production level CFD. And what you see is these are just my desktop here, and we're going to start with a plume study, and then let's actually start with the UAV case. So we've run a set of solutions at varying Mach numbers, and we're looking at how the performance of the system changes as a function of Mach alpha and beta. And we have about 27 or so solutions, and typically what people have done throughout the ages, really, for the last 20 years or so, is they do simple post-processing analysis. So this is the basic model. We're going to just look at the surface pressures to start. And you can kind of get a sense. We can look at the basic leading edge, look at the trailing edge. We can maybe pop in a slice in the Z direction, which actually is perpendicular to the wing. And perhaps we'll look at a few stream traces just to understand the fluid dynamics around the wing. Now, this is not atypical of way you might start your analysis with looking at a set of data. And what people have done up to this point is really use scripting. I mean, in effect, they would say, okay, cool, this is what I want. And perhaps they would do things like save what we call a layout. And then we'll put this over on the directory here, and we'll just call it test 1. And in effect, what they would do is then use the fact that the layout file has some text in it that you can then script around. And that is kind of cumbersome, and depending on the number of data sets you're trying to look at, usually people might look at 10 or 15 views, but it can be really complicated. And if you're the guy who wrote the script and someone else tries to use it, that's usually where you run into problems.
Right.
And that's an area where we started thinking about ways to make that whole process a little easier. So I'll take advantage of the fact that we have Tecplot Chorus, and I'm going to go ahead and load that in here. It looks like I might have 2 of those, so just for simplicity, let's just look at one. Okay, so this is the Tecplot Chorus interface. We're going to use this as a start point to bring in the results. And the results, we're going to create an entirely new project, and we're going to create a SQLite database. This is where we're going to store our information. I'll put it on the desktop, and we'll just call this My Course Projects 2. It's a flat file. It just links information about it contains the integrated quantities, as well as links to the information like the images I might create, or perhaps the physical data.
Yeah, I mean, it could also be a MySQL database if you wanted to, but SQLite is usually what you would use for a simple project like this.
At an enterprise level, it's probably better to use whatever if you're using MySQL. But for your typical engineer, that's probably unnecessary. So we're going to call this UAV test case 1 with, I think this is second order downwind. And then in the description, this might be, in fact, this was run with Fluent 12.2, I think, and I'm not sure. Actually, it could have been 13. I recently upgraded. So the idea is that you would start off by creating something descriptive, and then we're going to use the concept of a simple file crawler. So the idea, what we want to be able to do is be able to just crawl the data as simply as possible. And so we'll select that folder, which was the folder I just opened a second ago. And let's just go back to that to remind ourselves what we're looking at. We're actually looking at a series of just PLT files. In this case, they're Tecplot files. We have some additional files, including a CSV file. But none of these, I think, at this point, really, you could see that you'd have to write some scripts. In fact, I've already written a macro. And that's the way I originally ran this data. But we're going to take advantage of Chorus. We're going to load those data in. So we'll go down here to the meat of it, and we're going to identify the fact that we have mock number right there in the file name. Now, it's not limited to file name. Certainly, it could be just
folder
directed.
names, yeah.
Do you want to add anything to that? Okay. We'll also grab alpha and beta. So those are the independent variables that we changed. And you can see as we identify them here, they're actually pulled in directly from the data file.
Right, and you can see the colors change so that it really helps you identify what you're doing from where you're pulling the information from, the file name in this case.
And the next thing it's asking is, hey, do you want to link these files? Do they mean anything? In some cases, you may actually only have integrated quantities, but in this case, integrated quantities and/or images. But in this case, I have data. They all follow the PLT format, so this is just raw data. And we'll hit next. And then we want to basically go change the M underscore to something that makes more sense, like mock, alpha, and beta. And when we hit finish, what we've done then is actually created a project. So it just takes a minute or two. And what we have instead of a directory full of file names is we actually have, as you can see, a series of entries into our database. And if we now go to just one of them here, and we'll start off with just a simple example, we're looking at that same model, but it's tied now to my database, so that if I set up a simple, say, pressure contour on the wing, and say find a standard view that makes sense, like say maybe we just want to start with a simple view, edge on, leading edge. I'm going to save this template as T1P, and I'm going to go back into my system now, select all my results, and I'm going to create some plots that I can actually do some analysis with. So we'll start by looking at this T1P. We'll hit go, and what's going to happen is Tecplot Chorus then is going to manage the creation of these images. It doesn't limit it to images. If you have large data, you can also create surface plots.
Yeah, and that gives you more opportunities to rotate the data, for instance, and slice it to get the surface pressure profiles. But in this case, images makes a lot of sense. And actually, in many cases it does, because then you can, if you have 10,000 cases, I mean, it allows you to throw up this array of images and quickly move through you'll be demonstrating this, I'm sure, but move through your images and understand your results in a holistic way.
So if we want to look at multiple results, let's go ahead and just grab, say, the first 3 cases at Mach 0.1, and we'll go ahead and view the data now. And we'll take advantage of the fact that we have that template. And so here, instead of looking at one solution now, we're going to look at 3 solutions. And you can see they're all linked together. I can include my mock alpha and beta, which is kind of a good place to start. Yeah. I can move it around into any view I want. And then if I'm really interested in the delta P right here on the leading edge, I can grab, say, the base case, which would probably be, let's use this one at beta 0. And I'm going to do a quick difference. And now what we're going to look at is a quantified difference between these. Now you can see it's not that different. I'll change the color map to make this a little easier to see. So by using, say, a color map that's like the divergent red-blue, actually make sure we're looking in the right area. How about, there you go, I still can't see very well the difference. But the idea here is that if there is large differences, you can pick those up. And because this is Tecplot, I have the ability to go in and say, add additional contour variables until I start to see that variation. So you can start to see that here. So now that I have a little more variation with this, I can synchronize the styles across these, and now you can see that delta, where the real delta is on the wing. That's a very powerful way to look at subtle changes in the field data. Let's go back. I'd assume we're done here. Okay, it looks like our first job is completed. We'll go ahead and publish those into our database, and we'll evaluate the first set here. So what we're looking at now is a set of images at varying Mach numbers at varying alphas. So this is an alpha sweep going to alpha 30. And we're going to page these guys by beta, because we actually looked at different beta. So we can evaluate beta 10 and beta 20 versus beta 0. And although it doesn't look like there's much change here, there's in fact change. And if you would zoom in a bit, perhaps you could see that a little better. But this is a classic example of, I went through and I'm not seeing a lot of change. Maybe I need to change what I'm looking at.
Right, right. Now, in this case, you might actually go back and change your contour levels in your initial plot and redo it. But, you know, the goal here is to really, in this case, you've run these cases, and their first goal is to really verify that you've got good results. And until you do that, you can't really use this for analysis. So this is the technique for doing it is one technique for doing it is to use these images, and then when you see the array of images, you can actually draw some conclusions that would help you decide whether to keep that case or to exclude it from your analysis.
So here we're going to look at some fine structure. I've just dropped in a slice. I'll zoom out a bit so we can see that. And one of the things I did was add some additional contour levels. So again, to see the variation in pressure coming off the wing, coming off the leading edge and trailing edge of the wing. And also for simplicity, I'm going to add, say, 1 or 2, or say in this case, 10 stream traces, just to make sure that they look physically meaningful. Okay, so now we have yet another template. We can call this T2S for stream. And by hitting save, now I actually have those data. What I'm going to do in this context is go back into my original database here. I'll select all again. And now I'm going to create some images using my second template and hit OK. And it's going to go ahead and start to do that batch job. Now while it's doing that, I'm going to bring in some integrated quantities, because I really want to understand, well, give me the pressure on that wing. What is it actually, how is this vehicle behaving? Up to this point, we've looked at initial conditions, and although interesting, they don't really give us very much information. So let's go ahead and append the data using a CSV file. I'll browse over to the right directory, which I believe is on the desktop. Should be in the same folder. And here are the data we're going to select. And it's going to ask us to make sure we have the right folder. And then you can see that it has 2 things in there that it picked up our text. One is a file name. We don't need that. We already have a file name.
Right.
The other is, did this run complete? And that only means that did the simulator complete its job? Doesn't mean that it converged.
Right, right. It didn't crash.
Didn't crash. So if we want to keep that in this case it will show that they're all okay, but we can put that in as a run result, but we'll do that in a second. The other thing we're going to look at quickly is you can see that it has some variables that it identified, and it doesn't know, in effect, whether or not they are new variables or are they associated with what's already there. So if I put this in as Mach, you can see that it's identified, hey, you have Mach in your system. Cool, I will just associate this new data with Mach alpha, and you can see that that actually picked that up as well. And the same thing with beta. And now you can see that it understood that these are my independent variables, everything else being a dependent variable. When I hit finish, what changes is I've now appended to my data all the integrated quantities. So now my project has integrated quantities as well as simple initial conditions. It looks like my job is complete. I'll go ahead and deposit that right back into the database. So at this point, if we go back to this initial view, which we've identified as not being particularly valuable, we can apply that second set and perhaps get a little more interesting differencing between the different beta. So here's beta 0, beta 10, and beta 30. And right away when I look at this, these data don't look right to me. It looks, I'm not so sure I'd believe the way that the initial conditions were set up. And you didn't see that in the initial set of data. You kind of miss it. And that's really the power here.
Right. And, you know, the code said it completed, so you can't just go based on run successful. You know, you need to do further analysis to convince yourself that this is a good solution.
So in this context, if we wanted to then, say, take a look at this set of results, and you can see when I select them, it selects them directly out of my database, and I'm going to view the images for these results. Now, what I'm looking at is not really an array, it's actually the individual images for those set of data. And the thing I'm going to do is I'll change to that second set, which was more interesting.
Mm-hmm.
I can apply a label here. I'll just pop in a label here that shows the initial conditions because I want to be able to maintain those as I go across. And then I can select a file. So if I decided to look at the low, this is Mach 0.1, alpha 10, beta 10, 20, and I wanted to evaluate that against all the others that are beta 20. What I do is just say, okay, I want to make a difference from that data point. And now what we're looking at is a pixel difference from that initial case, which is at an alpha of 10, to each subsequent alpha.
Yeah, the advantage of the pixel difference is that it's very fast. And the second advantage is that it's insensitive to variations in the geometry. It'll show up, but it's a robust difference. And even if the geometry changes substantially, you can do that difference.
Mm-hmm. And which is, again, convenient if you're doing grid sensitivity analysis and you're more of an exploratory CFD practitioner, then you can actually use this image difference very quickly, even though you can't do a point-by-point difference.
Right. Yeah.
So we've talked about exploring just the fluid dynamics. Let's talk about some of the analytics by looking at the surfaces. So what we're looking at here is a 3D array, and we're looking at lift versus Mach and alpha, and this is the lift for the entire vehicle. We have the ability to change that. If we wanted to look at, say, lift for just one of the wings, we could do that, or the fuselage, we can do that. So here's the fuselage, and you can see a couple of things. We have the ability to filter on the independent variables or on other things. In this case, we're going to minimize the number of filters because what we want to do is look at different betas. So we're going to look at a single value filter for beta, and here are the three basic sets of data at the different beta stations from 0, 10, and 20. Mm-hmm. And the thing that we're going to do very quickly is apply a surrogate model. So we'll apply this surrogate model, and we're choosing a quadratic response surface. So here's our response surface for beta 0, for beta 10, and for beta 20. Mm-hmm. And one thing to point out, here's a good example where, although spatially it's difficult to see, I think if you look closely, though, it would appear that this particular model doesn't fit and I'm just going to make sure at the high alpha, which kind of makes sense because at an alpha of 30, this thing's probably not flying very well.
Right, you're going to be in stall range at an alpha of 30.
So this is, as a practitioner, what you might say is, okay, well maybe alpha 30 is too high. I may go back and run this, get a more robust study and limit alpha to 20 or 10.
Or if you need a response surface that actually, or not response surface, but a surrogate model that goes through that data, then you can convert to the kriging model.
Mm-hmm. Now just to extend this a little bit further, so we've talked about this nice case, and I actually picked this to start because it is a nice case. What happens when you get some results back that perhaps you're unsure of, and how can you take advantage of the same strategy? So I'm going to go back to my dashboard here, and I've actually run a few of these. And one of them is a toad, or what I'll call a code tuning example, where you're actually looking at a similar set of data, this ranging from Mach of 0.1 to 0.9. These are a similar UAV case. I've already run some images, and we're going to take a look at the same thing. So we're going to look at our response surface, so to speak, and doing the exact same type of operation. I'll get rid of my independent or my dependent variables, and what I'm going to do is just go back to that range filter and look at each of the beta surfaces and apply a surrogate model to this as well. So go ahead and grab those over. So we can now show the model. Here's the beta 0 case, the beta 10, and the beta 20. And what you'll see is that, again, there's areas where the data just do not sit well. They're basically way off the surrogate model. So there's not a good fit between these data.
Right.
And we can then further evaluate these data by taking a look at the data. We'll go back to a range filter here in that matrix view. And we're going to try to find an area where things just don't look like they're working correctly. So here's our first set of images. We can then go back to the stream traces, and we'll page this by beta, and we can walk and look at different beta. So right away, you say, whoa.
Yeah, what's that?
What's that? You know, again, going back to it, your solver may have converged, or at least thought it converged, but clearly this result doesn't look right. So we can then view all the images for that one data set, and suddenly you start to understand very quickly that, boy, that model doesn't make a lot of sense.
Yeah, and if you view the data on that, you'll see that in this case, there's clearly this pressure wave. You saw that a little bit in one of the images, but there's this pressure wave that is coming from the downstream boundary up, and so this is probably in the process of failing. It just hasn't failed yet. You can see that very high pressure downstream of the vehicle, and so it's this is a case you would want to remove from your analysis.
And that's a good point, Scott, because when you are looking at your surrogate model, and we'll go back to that surrogate model for a moment, you can see this is the data point in question.
Right.
And we'll go back to a single value filter here so we can look at it in more detail. Okay. There's the data point in question. You can see it's way off. What I'd like to be able to do in this case is say, you know what, we're going to make this inactive or active. And so in this case, I'm going to set it as active just to show you. And we're going to put case status over here so that you can see it. So here's an active point. If I want to make this inactive, now you can see that I've got these active points and inactive points, that if I want to take this off, I can actually remove it from the data.
Right.
Which would be kind of convenient if you're looking at those cases. So, okay, so we're at about 32 minutes, and our goal is to make sure that we have plenty of time to review, in this case, questions. We already have a couple of questions queued up. As we're going through, if you have any additional questions, now is a good time to start queuing those up so that when we get into Q&A, we can spend some time on it. Okay, let's now go back and talk about a slightly different type of analysis where we're not going to be looking at something as aerospace specific. We're going to look at plume migration. Just to give you an idea, this is a test case. It was a manufacturing plant, and what they're primarily interested in is the SO2 plume migration through this domain. And so I'm going to pop into, you can see the contour pressure. It's really not that relevant for this particular example. What we do care about is the SO2 concentration. You can see it's very low. And I don't know which one I chose, but we can again go through and you can just start to add some contour levels just by clicking on the flow domain. And what we're doing is really just refining the fine structure. And since we're talking about extraordinarily low concentrations of SO2 gas, you need to do that.
Right. Now the idea here is to actually run these cases with a variety of wind conditions, right, so that you can see what this pollutant will do and who it will impact.
So if I take the same analogy, if we look at this as, okay, well, how are we going to then go through the 16 plus variations and understand what they mean? Remember, we have the same problem, and then we've got a whole bunch of files, and we're not going to go through and do this using the old method, which would have been scripting it. We're going to go ahead and use Chorus. So we'll pop in, we're going to create a new project. We'll discard what we've done already, and we'll use the same SQLite database, and we'll just call this project SO2. I've already done this once. And we're going to use a CSV file importer. So instead of actually going through and using a file crawler, we're going to just start with a CSV file which we've already created in advance. So let me go ahead and grab that. And this is the output from the integration. I believe is the correct one. Go ahead and hit open. And let's go make sure we're in the right directory. And you can see that in this case there is a file name, and we'll call this raw data. And it doesn't really know what's independent or dependent. So in this case, we're changing the prevailing wind conditions and the SO2 concentration. And when I hit OK, you can see that it's created a project. Again, we now have the integrated quantities. And for any one of these, I can view the data. And what Tecplot Chorus allows me to do then is to go through and set up my style. Now, if I were to save this style, which actually I'm not going to, because let's at least put on something like a contour and turn off the mesh and perhaps do just what we did before, which were to change this to SO2, turn off translucency. You can see right there next to the exhaust port we have a higher concentration of SO2 as you would expect. We're going to add some additional contour variables, just looking basically at ground level. And let's go ahead and set this up as our initial view. Save that as a template as initial view. And now we can do the same thing we did before. Select all our results. We're going to create some images based on this initial view. And we're also going to create some data based on the initial view. And what this is going to be is just simple surface data. In fact, let's go ahead and make it ever so slightly more interesting by, say, put on an isosurface, something a little more interesting than this. So you can see the small isosurface there. I'm just going to change the concentration. We're going to go up go down 2 orders of magnitude. And from a style perspective, we're going to change this to just show red, and in this case, or pink. This is good enough. Pink is bad. You don't want to find yourself there, if at all possible, because it will get you quite sick.
Stay out of the pink gas.
Stay out of the pink gas, if at all possible. Okay. This is our template, and we'll actually call this SV for second view. Of course, you'd probably want to be a little more descriptive, but in the interest of time, it's not important. And we're going to go back here, and now we're going to create data themselves. We're going to create surface data using the SV, and we're going to say OK, and I'll show you why here in a second. In the meantime, my PNG, or the image creation, is done. And if I then look at the data, I can look at this, what we call a matrix view, where I want to look at, say, SO2 concentration on the top as a function of, say, the northeasterly winds. And so you can see quickly how the data are changing. So you can see we have quite a few results here. And of course, if I select the lowest concentration at the lowest northeasterly wind, I can see where that data falls. And if I, say, just select all these data right here and view images, then I can do a quick difference from my base image. And now I'm looking at what the net impact is of changing the SO2 concentration or the prevailing winds. Mm-hmm. Looks like my job is complete. I'll go ahead and deposit my data. And now we're going to go in and we're going to evaluate all the data we have using this new surface file. Now I'm going to show you this because, in fact, even though I'm only looking at 16 results, you can see how quick it really is to look at these data. So here we go. Which one is this? Must be this one. Okay. You can see the data is already loaded in Tecplot because these data are extraordinarily small. We went, I think it's 1 megabyte.
Yeah, it's Tecplot 360 can handle quite large files, and these are not very large at all.
Well, these are the surface files.
That's right, yeah.
They're extraordinarily small. So
yeah.
We'll go ahead and put those here. Now, this is kind of an interesting way to look at the data because now we can interact with it. And we can see how it varies. So if I want to understand what the northeasterly winds and SO2 concentrations are. I can put those right on the image, and I'll synchronize these guys so you can see this. So you can see we can create this nice array of plots, and if I want to put these into, say, a PowerPoint or dump these out as an image, I can then export this as, say, well, I don't know, it really doesn't make a bitmap. It's not critical. All the frames, and then I can control that resolution, make it, say, 3000, and we'll put it right out on the desktop. Save that. And in principle, you can get to the desktop. We should have an image. And now you have a nice high-quality image. And if you zoom in, you can see just how high-quality this image really is. We have to give. So here's you could actually look at each individual image in detail.
And this is important for reporting and to have the presentation quality because in the end, most people end up generating some sort of report or presentation based on their data. And to have this sort of quality is very helpful.
So we've talked about really two basic use cases where we're looking at parametric space. Of course, we could walk through a couple of others that are more time dependent. What I wanted to show you is that, in fact, you can apply this methodology to a number of things. For example, we're going to just load a session here. I can also look at blade optimization. So here's an example where we're looking at a time resolved solution where time is at the top here, and what you're looking at are 5 different blade configurations, and the mesh is different for each one of these. So at t equals 0, if I view all the images at t equals 0, and we'll go to the second view so it's consistent, I can do a comparison, whereas before I really couldn't because these mesh aren't the same. So it really gives you a lot of power for looking at things that are even time resolved. If I want to look at just one blade configuration, I can look at it almost as an animation as well, just by going down. So here are the data, and I know it doesn't update perfectly for you, by the way. I can see the update. Apologize in advance, I'm going too fast. I'll go a little slower. It's actually not that bad.
No. And you have a lot of control here. You know, adding time as a parameter gives you a lot of ability to do comparisons that you couldn't if you were just, for instance, comparing animations.
Right.
And so it's a very powerful analysis tool.
In addition, if we wanted to do a little more, I'd say more quantified look at the data, we're going to evaluate, say, as a function of time step. Let's look at, say, the total integrated quantity per blade. So we'll group these by blade, and we're going to sort them by time. So what you're looking at here is each one of these curves represents the pressure, the total pressure on all 3 blades for a different blade configuration. And as a result, I can actually go up here. Let's see here. Sorry. And look at a single value filter, and now I can walk through each blade. So we can see, in this case, we have blade 4 seems to perform much better than say, blade 1, 2, 3, or 4, I guess, in this case, and 5. So again, you can really start to explore the performance space of a given vehicle, or in this case, an optimization. Okay, let's pop back in here. So we talked a little bit about model refinement and performance prediction using Tecplot Chorus. We walked through in detail how to create these type of projects, and we showed you can start with CSV files or you can start with file crawling, and we showed you how to create, in effect, images that you can use in PowerPoint presentations or whatever other communication vehicle you use. So I think at this point what we'd like to do is turn it over to questions. As I said, we wanted to make sure that we had plenty of time. So with that, a couple of things. For those of you who will be attending the AIAA meeting in January in Nashville this year, Keep wanting to say Reno, but we know we've moved on. We're not
We're
in Reno.
showing our age.
Can't even say Orlando anymore. Just got used to that. We are actually going to be having a sneak peek party for those people who are going to be attending. It's 10. Let's see. I'm saying on the 10th at 8 p.m. I believe, and I could be wrong. It might be 7:30, but
it is on the 10th, though. Yes,
definitely on the 10th, and we believe it's at 8 o'clock. The other thing is, if you're interested and you'd like to take a look at Chorus, we will make Chorus available to you, as well as some of the test data. If you're interested in the test data we use today, we'll make that available as well. Or if you want, you can contact either Scott or I directly. Scott Imlay, s.imlay@tecplot.com, or me, Darrell Rittenberg, at d.rittenberg@tecplot.com.
And I would add, I'm actually presenting a paper at Nashville. If it's on the last session of the last day, but if you'd like to come see it, it's on a new visualization technique for metadata. Be happy to have you there.
And Scott, I believe that's something we talked about in one of these webinars, which was the generalized box plot.
That's right.
Correct?
Yeah.
So if you're interested, that's a very interesting topic, way to apply some statistical methodologies to a series of integrated quantities.
Yeah, highly dimensional data. It's very difficult to visualize 5, 6, 7, 8, 10 dimensions. This is a technique that gives you a holistic view of your 10-dimensional data, and so it's eventually it'll make it into Chorus, and it'll be part of our product.
And I've just been asked to make a note. Yes, it is at 8 p.m., and we'll be giving out T-shirts, as well as we have a chocolate fountain and dessert, too, apparently.
Ooh.
Ooh. Didn't even know
I'm going to be there.
Hey, me too. Okay, well, let's go ahead and open it up to questions. Two things you can do. If you have a question and you'd like to just raise your hand over on your sidebar, you'll see an area where it says raise your hand. If you raise your hand, we can call on you and unmute you, and you can just directly ask a question. We do have a couple of questions queued up here, but I'll give you a second to collect. We'll see if we can make this bigger on our screen so that we can see you. Okay. All right. Let's start up at the top. It says, when you add a contour by picking a point, then generate a layout and apply that new layout, does the contour level remain fixed? The answer is yes.
Yes,
It is definitely fixed. The thing about what we talked about briefly, Andrew, since I happen to know who asked the question here, is if we go back here, a style file that is what Tecplot 360 is actually saving out includes the information about the style necessary to create the plot here. So I think one of the things that you can do is, if in fact, because it's a text file, you can actually edit it if you had a set of contours that you wanted to put in. So, but it's maintained across.
Yeah, the contour levels are in the style file.
There was another question again about surrogate models. Man, I tell you, people really want to know more about it. There was a question about whether or not the API for surrogate models will be open. I think that's our intent. And Scott, I don't know if you want to talk to that at all.
Oh, definitely. We have had a lot of interest in that. People want to add their own surrogate models. It's something that's kind of personalized, I guess, or at least institutionalized between companies. So we will be making an open API for our surrogate models in the future.
Another classic question, how does it perform with large data? Boy, I wish I had some big data to show you here. This particular, it's actually interesting for those people who might be interested in kind of how we're running here today. We're actually running on a virtualized desktop environment that's out on our server. It's a new technology, and we're running with that technology. I wonder if I can actually show you what my resources are. I'm not sure if I can or not, honestly. But computer. Okay, I'm not sure if I can actually get my computer information here or not. I'm going to go to properties. Okay. Yep. So this gives you an idea. Because I'm running on this virtualized environment, I have 48 gigs of RAM, Boy, it looks like I guess I only have 2 processors, but that's okay.
Right, 2 processors. I believe it's 8 cores total.
Mm-hmm.
Yeah, so this is a VMware based virtualized machine. It actually is mapping to hardware graphics, so it does have graphics hardware acceleration. And the interesting thing about this is I've run this from home, and I've been able to visualize cases from home that are 500 million cells. Mm-hmm. And half a billion cells, and it's just like being in the office. Yeah. So it's a very cool technology. It's something that people should be thinking about.
And in fact, it allows you to do things like, if I show the dashboard here, and I'm not sure which one of these would be the biggest, perhaps. Maybe this one. Okay, so here's an example where you have 32 simulations. I can actually view all of them just using, okay, SV is fine. Say OK. And now I can actually load those in. You can see how quickly it's actually opening up. In this case, we're opening up all the 32 simulation results into Tecplot on this machine, and it's pretty darn fast. Once it redraws, we are talking, they're going to be very small, unfortunately, because it's trying to put all 32 frames side
on
by
the
side.
screen, yeah.
But they're there, I promise. Yeah. We can actually make them a little easier to see, I guess. And then we'll just put that. Oops. Put that a little bigger. So if you zoom in, you can see that the images themselves or you can see the actual model, and you can interact with it, and it's really fast. So very fast, amazing technology, this VDI technology. And we're going to be putting on a webinar about this in the early part of next year. We'll talk more about and have a couple of the folks from our IT group talk about this as a potential strategy for handling very large remote data.
Yeah, exactly. I think on the performance side, it's worth pointing out that this is based on 360 technology. This is actually Tecplot 360 running here. And 360 has improved performance tremendously over the years. If you're still running Tecplot version 10 or something, it's really worth getting the new one because it's probably an order of magnitude faster in most cases.
Maybe even more.
Yeah, and so it's no comparison. And we every year we seem to do another factor of 2 or 3. So it's really is a fast visualization package now.
Yeah, it's amazing what we've been able to do. Okay. Again, if you want to raise your hand, we have a few more minutes for questions. Okay, there's another question. In this case, it's about the output, or someone had asked about this little thing here, this tiling. This is in Tecplot 360 circa 2011, Scott, I believe is when it was put in. Mm-hmm. It just allows you to kind of play around with how you manage frames on screen. So just a nifty tool that was in there. The other thing that allowed you to do, if we just go back to one result, and without a template. Okay, well, even on this one it's fine. The other thing that it added was the ability to do kind of projection views or projected views. So now we're looking at the principal views, the XY, the YZ, and XZ. So
yeah, traditional engineering plotting.
Yeah,
it
simplifies that process quite a bit, and you can go right back to your initial view. You can also play around with how it's done, but neither here nor there. Can you create a movie from transient data? Good question. That's in the backlog. It isn't available in the current version, but it's on the backlog. You could do it now, but it's kind of kludgy.
Right. That is a direction we're going. Now, I'm assuming that this question is about doing it in the Chorus product and not within 360. Clearly, you can do it within 360, but yeah, within Chorus, that's a feature that's coming soon.
Okay, we have time for perhaps one more question. So if you have a question, you can go ahead and answer or ask that. Okay. Well, it looks like I think we've answered most of the questions. This recording will be available very soon up on the web, so you'll be able to go back through it. The other thing that will be available, there'll be a couple of recordings of kind of what I did in little bite-sized chunks, creating a project. We do have a series of videos that are already online, but we'll add a couple more. So if you're interested in giving this a go, let's see, you'll be able to take a look at both the data and the tool. There's one last question as we head out here is when will it be available for OS X? And I know that's on the backlog, but I'm not sure.
On the Mac.
Yeah.
I mean, it's running in-house on the Mac, and I'm not certain when it's going to be released, but I know it will be.
Okay. Well, again, let me thank Scott Emily for joining me here today.
And thank you, Darrell.
And also to thank all of you. Enjoyed having you on, and appreciate your continued interest in learning about simulation analytics. Look forward to our next series of talks, which we will be focused on continuing on simulation analytics as well as large data processing.
Yes.
Thank you very much, and for some of you, we'll see you in Nashville.
Take care.